Hello, K Squid listeners. It's every other Sunday again, and you're listening to Sustainability Now, a bi-weekly K Squid radio show focused on environment, sustainability, and social justice in the Monterey Bay region, California, and the world. I'm your host, Ronnie Lipschitz. The world is awash in plastics. According to a study published in 2020, total production of plastics since 1950 is now over 10 billion tons, with more than half of that simply discarded. And the production of plastics will only increase in the future. There is a lot of oil and natural gas in the world, and if and when we wean ourselves from fossil fuels, oil and chemical companies will be looking for other places to use their stocks. So far, only about 1 billion tons of plastic have been recycled, that is, put into the recycling chain. What exactly has happened to that material is less clear. Different types of plastic require different post-consumer processing to turn them back into pellets of raw material. Most factories are set up to use only particular types of plastic, and it is still cheaper to buy virgin pellets than recycled ones. Maybe compostable plastics are the solution. But what is a compostable plastic? What is it made from? How is it broken down? Are there plastics that will simply decompose into constituent molecules by weathering and microorganisms? Questions, questions. Are there any answers? My guest today is Dr. Susannah Scott, Distinguished Professor of Chemical Engineering, and occupant of the Duncan and Suzanne Mellichamp Chair in Sustainable Catalytic Processing at the University of California, Santa Barbara. Here I quote from a UCSB website. Her research interests include the design of heterogeneous catalysts with well-defined active sites for the efficient conversion of conventional and new feedstocks, as well as environmental catalysts to promote air and water quality. We're going to have a more prosaic conversation today about the chemistry of plastics and the challenges to recycling and composting them. Professor Susannah Scott, thank you for being my guest on Sustainability Now.
Thank you for the invitation, Ronnie. I'm glad to be here.
So why don't we begin with some background? How do you describe your research to those of us who never got much beyond college chemistry? What exactly is sustainable catalytic processing?
Well, I'm a chemist by training. I'm a professor of chemical engineering at UC Santa Barbara, and my specialty is the field of catalysis. So I've worked in this field for a long time. Catalysis is the transformation of one type of molecule into another type of molecule, or one material into another material, and trying to accelerate those transformations and make them as selective as possible is the role of this substance we call the catalyst. Mm-hmm. So I design catalysts. Everybody in my field now is working to enable the energy transition and the materials transition. That means that all of the catalysts that we have designed and optimized over decades to make all the things that people use out of fossil carbon, now we have to re-engineer them, redesign them, so that we can make them out of renewable carbon. And we have to redesign the processes to use renewable energy to make these transformations happen. So sustainable catalysis is catalysis with that lens added, that we want to be able to use renewable carbon to do it, and we want to reduce the energy footprint as much as possible and use distributed renewable energy.
Well, given that most of our listeners probably didn't get beyond college chemistry, what are plastics made of? How many kinds are there? And could you explain to us how different molecular structures result in different types of plastic?
Sure. Plastics are basically organic materials. Organic meaning they're made out of carbon. Carbon is the principal component. There's usually some hydrogen, there's often some oxygen, some nitrogen, so there can be other components, but mostly it's carbon, which is why we call them organic materials. And they're made using catalysts, which is, my particular expertise of being able to synthesize different kinds of plastics by manipulating the carbon atoms. And to make a plastic, what you do is link together thousands of carbon atoms in a very, very long chain. and you do this with many, many chains, and you have a material which has very unique properties. The properties depend on how you make the chains. It depends on what kind of atoms are in the chains. If you look at the recycling symbols on the bottom of plastic pieces, there are 7 different numbers. Basically, there are 6 large types of plastics, and then everything else is in the category number 7, which means there's really many, many more than 7 types of plastics. There are dozens of types of plastics, and each one is subdivided into many grades, we call them. So polyethylene is not just one material, it's actually many types of materials that are all designed for different purposes. So when people think of plastic and plastic recycling, it's unfortunate to give the impression that it's one material. It's not. It's hundreds of materials, and each of them have different properties and different challenges for recycling.
Well, so those of us who recycle look at the numbers, but the numbers then are really sort of categories of numbers of different types. Is that correct?
They're groups. They're
Yeah.
definitely groups, right? And so the problem is that if you would combine a piece of polyethylene that came from a milk jug with a piece of polyethylene that came from a film, you're talking about different kinds of molecules, different lengths, different distributions of lengths, different types of branches on those chains. And if you just mix them together, you'll end up with a material that does not behave like a milk jug, and it doesn't behave like a film. It's just something that isn't very useful. That's the challenge of plastic recycling.
Yeah. Just to go back to the catalysis part of it. I mean, most plastics are made from oil and natural gas, right? At this point. And
They
I'm
are.
just curious, I mean, oil has to be broken down into fractions as well. Which particular fraction does the feedstock for plastics come from when oil is being broken down?
So conventionally, it's the naphtha component,
Uh-huh.
which is the lighter molecules. And
Mhm.
they have to be cracked. The oil that comes out of the ground is a hydrocarbon that contains a lot of hydrogen. And we have to remove some of that hydrogen in order to link the molecules together to make a molecule that becomes a plastic.
Mhm.
That really changed about a decade ago. And that was the shale gas revolution. Now we get most of the carbon that we put into plastics from components of natural gas.
Mhm. That's easier to break fractionate the
Um,
gas, or is it just a supply issue?
it's basically a supply and cost issue. This is
Uh-huh.
a low
Okay.
cost form, a really low cost form of carbon, and it's very, very clean relative to the kind of stuff that comes
Oh.
out of the ground as oil. So you have to clean it up less.
Well, is plastic, a generic term that's used to describe the properties of a broad category of materials, or does it refer to the particular molecules, that we've just been talking about? Because of course we say, something is very plastic, and I know that there are some terms applied to materials as well.
Right. So, I mean, what the public knows as plastic is really a class of materials that scientists call thermoplastics. And
Uh-huh.
thermoplastics are materials, the thermo part is heating, right? So when you heat a thermoplastic, it becomes soft and eventually it will melt. What that means is that you can mold it into a variety of different shapes. All you have to do is heat it past this temperature when it softens, and then you can make all kinds of things out of it. So you can make bottles and films and chairs and anything that you like.
Mhm.
Um, and so these organic molecules, because um, they're very long and flexible, and they have properties that allow them to melt and then re-solidify. This is what gives them this thermoplastic behavior.
Mhm. Okay. I was doing a little bit of research into the history of plastics and discovered that the first one ever made was Bakelite, and I actually remember things made of Bakelite. I'm old enough for that. But what was that made of, and is it still around?
The Bakelite is a really interesting story. it was an American entrepreneur who came up with this material and found some uses for it. It's about a century ago now.
Hmm.
It's not actually a plastic, even though
Oh,
everybody thinks of it as plastic, but it's a different kind of organic material called a thermoset. So remember that a thermoplastic is a material that softens when you heat it. A thermoset is an organic material that becomes hard when you heat it. So you can't melt Bakelite. It doesn't melt. It doesn't soften. Um, I interacted with Bakelite when I was a kid as an amateur musician in the school orchestra. I played the oboe. And so if you
uh-huh.
can imagine what an oboe looks like, or a
Yeah,
clarinet or a
yeah.
bassoon, those ones, at least the ones that are made out of plastic, are actually made of something very close to Bakelite.
Well, that's
That's the stuff,
interesting.
that black hard stuff.
I know that telephones were made for a long time were made out of Bakelite. Um,
That's
and when
right.
you were talking about that, it I remembered this scene in Failsafe where the president's phone melts and emits a screech. So actually, it probably didn't melt, right?
Probably
Um,
didn't melt.
again, some of us remember that kind of stuff. Well, let's turn to recycling because that's something that obsesses almost everyone. It's in fact become something of a religion, at least in parts of the United States. But most plastic ends up in landfills or the environment. So why is that?
So I think we have to remember that these plastic materials are very highly engineered to have very specific properties. So you can do that if you start with a clean raw material, and you manufacture the plastic to have very precise molecular properties. If you take mixed municipal waste, which is different kinds of plastics, as well as other materials and all kinds of trash mixed in, you have to collect it, you have to sort it, you have to clean it, and then you can maybe, if it's clean enough, recycle it and make something new out of it. All of those extra steps cost money and they cost somebody's time to do them. So we're in a position now where the recycled plastic, the high quality stuff, actually costs more to produce than the virgin plastic that's made directly from shale gas. And of course, there are people who are willing to pay more so that something is made from recycled plastic, but for the most part, the value proposition is pretty poor for recycled plastics. On top of that, the recycled plastics will not be engineered to have precisely the properties that you want. When you mix different grades, even different grades of polyethylene together, or if you were to mix polyethylene and polypropylene together, you'd end up with a material that did not have the precise characteristics that you want for the application. So most of the recycled plastic ends up in things that they're very tolerant of variations in properties. You can make carpets or playground equipment or plastic lumber. This is called downcycling.
Mhm.
So, we don't have very high quality requirements for those applications, and you can use recycled plastic to do those kinds of things. But if you're talking about healthcare applications, food grade plastics, um, apparel, those kinds of things, the purity requirements are much higher and the property requirements are much stricter, and it's very hard to get enough high quality material, high quality plastic to recycle.
So two thoughts arise. First of all, the demand, I guess, for this recycled stuff, if it's recycled into playground equipment and plastic wood and things like that, I guess it's not high enough to make it worthwhile to do more of the processing of the plastic waste. Is that accurate?
I think that's accurate because it does cost money to collect the stuff and to sort it and clean it, and then you're going to sell it in a very low value
Yeah.
application.
Uh-huh.
So the economics are not very good for this.
I mean, I know that China used to take a lot of our plastics, and then they institute. I think it was called a national sword policy. I had shows on this before, and I can't remember that. What did the Chinese do with the plastic at the time?
Yeah, so that's a good question. I mean, until 2016, the entire world exported its plastic waste to China. And I assume that they sorted through it and picked out the pieces that they had some value for, which was a small part of all of the plastic waste. The rest of it they would have buried or incinerated or something like that.
Mm,
I mean,
mm,
basically, as long as it was out of our sight, we weren't thinking very
yeah.
much about it. And as soon as they banned that practice of taking in the world's trash and sifting through it to find some value in it, um, it woke everybody up in terms of we're not actually recycling.
Yeah, yeah. So most of the stuff still ends up in landfills. Most of the plastic ends up back in landfills.
It depends where you live. In the US, most of our plastic goes to landfills. In Europe, in Japan, where they have much less space for landfills, most of the plastic gets incinerated.
Mm,
If you burn it, of course, it's an energy rich material. It's an organic material, and you can combust it and you get some energy recovery. So that's something. And it keeps it out of the landfills. But there are problems associated with incineration as well. Of course, you're making CO2, which is undesirable. And there are other combustion products which can be toxic or hazardous that you don't want to release. And so um, you have to protect the air quality as well when you're doing plastics incineration.
You're listening to Sustainability Now. I'm your host, Ronnie Lipschitz, and my guest today is Dr. Susannah Scott from UC Santa Barbara, who does research on catalysis and particularly is focused on plastics, on the trying to find as I said in The Graduate, right? Plastics, the plastic that will save us from ourselves, I guess, is the word. Now, one of the other problems is that the manufacturing industry is largely tooled for the virgin raw materials, right?
That's true.
That's true. And I mean, what would be required to retool production for recycled plastic?
Well, so these long organic molecules, the plastic molecules, undergo a variety of transformations when you make stuff out of them. They can undergo chain cleavage, so the molecules get shorter. They can undergo cross-linking, meaning the molecules get longer. If you're mixing together different lengths of molecules in the first place because they came out of the trash and you weren't really controlling the types of plastics that came in, you would have a hard time getting the right properties out of the plastic that you're trying to recycle. So what people are talking about now is blending virgin plastic with recycled plastic to make sure that you get the right properties. That means you have to be monitoring what's coming in and monitoring the properties of what you're making in real time so that you can adjust the blends. And I think that's an interesting approach. It adds cost, of course, if you're going to do these extra steps. Um, and it doesn't eliminate the need for virgin raw material.
Yeah, of which there's basically an endless amount, given the supply of fossil fuels, right? As I mentioned in my introduction, if we wean ourselves off of fossil fuels, the companies that own this stuff will want to find other uses for it. Um,
Well, the use of plastic worldwide is growing.
right.
These are very cheap, very versatile, very useful materials. So there are lots of uses for them. And as we start to think about replacements and the cost and the challenge of making replacements, they're going to have to compete against these very cheap, versatile materials. So it's a challenge to find ways to make this a solution that people want.
That basically is cheap and convenient, low cost and convenient, right?
Exactly. Yes.
Exactly. Yeah. Um, I don't remember if it was you or someone else that I heard this from, but one suggestion was to reduce the variety of plastics produced in order to make separation easier. Is that something that would be feasible? Assuming there was the incentive, some incentive to do this. I don't like to use the term will, but there's some incentive. I mean, would that help in terms of recycling, or are there too many varieties to make this possible?
Well, So what we've seen over the last 50 or 60 years, which is the basically the life cycle of really commercially useful plastics, is an incredible proliferation of designs because these are designer molecules.
Hmm.
Chemists and material scientists can make all kinds of plastics and make them for all kinds of uses. So they can optimize the properties with basically no restrictions on what they use and no thought for what happens to them at the end of life. That simply wasn't it wasn't the problem because nobody was trying to get them back at end of life and reuse them. If there were incentives to get them back or regulations that said producers had to take them back, they would immediately be incentivized to find ways to make it easier to recycle them. And that certainly would be enabled by having fewer different types of plastic. You'd like, for example, not to have to mix or to unmix polyethylene and PVC, polyvinyl chloride. PVC, the chloride that it contains really messes up the recycling of other kinds of plastics. And so if we just didn't have PVC anymore and made everything that we used to make out of PVC, we made it out of polyethylene instead, it would be easier to recycle the polyethylene. You could actually make the same argument about all the additives which are put into the polymers to modify their properties, right? So it's the way that we design plastics is not just the plastic, but all the other things that go with the plastic to make it behave exactly the way we want it to behave. And some of those additives also are really poor for recycling. They build up as we recycle and they alter the properties of the recycled material in unanticipated ways. So I think what we will see is a down selection of the number of types of plastic and also some regulation on which additives you're allowed to include and which you can't include, precisely because they affect recycling.
Well, no, I mean, that's an interesting point. Why do you think that we will see that regulation and what did you call it? Not downcycling, reduction of
Well, a reduction.
I mean, I haven't seen any sort of indication that outside of, let's say, research labs, is this going on anywhere? Is it?
So I actually have many colleagues who work in the chemical industry, and I
Uh-huh.
talk to people who make these plastics. And those companies are actually very concerned about the future of the industry and
Uh-huh.
what it will take to make those materials less impactful on the environment. So, I mean, I think they're thinking themselves about how they need to adjust. Their business model is at stake, obviously, so that would
Right,
make sense
right.
if they were to do that. They're also trying to anticipate what regulations might be put in place. And so, we're seeing people talking, even in California, about banning single-use plastics, and plastic bags are banned in places, plastic straws are banned in places. There will be bans, but I think it's completely unrealistic to have a complete ban on plastics.
Mm-hmm. Mm-hmm.
There just are not reasonable replacements for some uses. And in those cases, probably we're going to start seeing what we call extended producer responsibility. So
Mm-hmm.
you will be allowed to manufacture those things and sell those things because there's an essential need for them, but you have to plan for their end of life, which could mean taking them back again and turning them into new materials or doing something else that is not going to let them leak into the environment.
So the incentive there for a company would be if they have to take it back, they better make it as reusable as possible, right? I mean, I suppose, reduce the complications and the additives and things like that.
Yes, exactly.
Uh-huh.
Yeah, and
Mm.
there are shoe companies now, Nike and Adidas, that are talking about these kinds of strategies. If you can make your shoe out of one kind of plastic, and then you can have your customers, when the shoe is old and worn out, bring them back, and you'll trade them in and give them a new pair, and take their old pair back and disassemble the shoe and get the plastic back and make new shoes out of it. That would be a different kind of business model.
Yeah, well, it sort of sounds a bit like the iPhone model, right? Which is, we'll give you something for your old iPhone as long as you pay us more for the new one. But but I'm being cynical here. Well, let's
Well, and
turn.
I don't think the iPhones get recycled either. So
No, no, I don't. No, you wonder where all of that stuff goes. Um, Well, let's turn to decomposition, okay? Because I mean
Yeah.
that's a big issue now, right? We find microplastics in our bloodstreams and places like that. So what happens to plastic after it's been used? Besides the recycle, I mean, chemically and physically.
Yeah. So, I mean, some plastics, many plastics are incredibly robust materials.
Hmm.
They're long chains made of carbon-carbon bonds, which break down extremely slowly from natural causes. These plastics can endure in the environment for we don't know how long, probably longer than plastics have even existed. So if you try to estimate lifetimes, it's a fraught calculation because we don't actually know how long they live. But um, there are, faster than those kind of chemical processes that break the molecules into small pieces, there are weathering effects.
Mm.
So, a piece of plastic bobbing around on the surface of the ocean, being exposed to UV radiation, bumping into other things, it's going to fragment into pieces, and those pieces get smaller and smaller with time. That's where a lot of the microplastics are coming from. A lot of them come from things like tires, which undergo abrasion and attrition when we drive our cars. They come from our clothes when they're made from synthetic fibers, and we wash them, and there's abrasion in the washing machine, and little pieces of plastic chip off. We don't actually know how long those very small pieces of plastic live. So right now we can only say we can detect them. And being able to detect something doesn't mean that it's dangerous. It doesn't mean that it's long-lived. It just means that you can detect it. This is a very new science, and it's astonishing that we can detect these things in as many places as we can. It's a symptom of how widespread the use of these materials has become. They've
Yeah,
become so universal now that you can find them everywhere.
you can find them everywhere. I'm sort of curious. You're talking about long chains and long lifetimes, but obviously the pieces break up, right? As you say, under weathering. So I'm curious. I mean, in crystals, it's the electronic bonds that keeps things together. What keeps the plastic together? Um, I mean, how are molecules then, linked to each other?
Well, in thermoplastics, the molecules are not linked to each other. Each molecule is a separate molecule, and they're,
Uh-huh.
you know, they're sort of packed together. They can be crystalline, even though they're not chemically bonded to each other. But most of the durability of these molecules comes from the fact that they repel water very, very strongly. So,
Uh-huh.
um,
And of
the
course,
kind
water is the enemy of everything.
water breaks things down.
Yeah.
They're very non-polar materials. That's what we call them. Hydrophobic. They repel water, and so you can't get in and break those carbon-carbon bonds in the polymer backbones very readily, and that just gives them very long lifetimes. Microorganisms can't decompose them very readily either because they're not soluble. So, they're
Mhm.
they're the same kind of molecules that you find in oil, but an oil spill on a beach or on the surface of the ocean will eventually break down. Microorganisms will break down these molecules when they get to uh, about 1,000 carbons or smaller. But the molecules in plastics have 10 or 100 times more carbon atoms than that.
Hmm. Wow. You're listening to Sustainability Now. I'm Ronnie Lipschutz, and my guest today is Dr. Susannah Scott, who works on the catalyzation of plastics and other materials. And we've just been talking about how plastics break down, not decompose. I want to go next to decomposition, which is not quite the same, right, as breaking down. Breaking down is just smaller and smaller, smaller bits,
Right.
right? Whereas decomposition is the actual breaking of the carbon chains.
Yes. So we,
Right.
we want to turn them into molecules to break them down,
Okay.
small molecules.
So decomposition would basically be, well, would you develop some sort of chemical process then? I mean, in one world to break them down, or would you rely on biological processes?
Well,
If
microplastics that are dispersed out in the ocean, I think are going to be impossible to recover, right? We can't sieve the ocean. So eventually those will be broken down through biological processes, very, very slow processes, where microbes will colonize the surface of the microplastic and eventually start to eat into it. It gets a little bit oxidized, naturally bobbing around in the water, and then microbes can actually grab onto it and break it down. So the ultimate fate of all of these materials, because they're made of carbon, hydrogen, and oxygen, is going to be CO2 and water. And
Hmm.
those are molecules which are harmless once you
Hmm.
get there, right?
Yeah.
It's an extremely slow process.
Yeah.
You can accelerate that process in the lab. Obviously, you can design a catalyst that will turn these molecules into those small molecules very quickly. But it, molecules which are or plastics that are designed to be used out in the environment. I'm thinking of fishing nets and things like that. Um, these materials need to be made in a way that they don't persist in the environment for centuries.
But at the same time, they need to be robust enough so that they don't break down quickly, right? I mean,
That's
that's
the
it's
challenge.
a trade-off, a real
Right.
trade-off there,
I
right?
mean, originally fishing nets were made from hemp and
Well,
natural materials like that. And fishermen were constantly repairing them because they were decomposing on the same time scale that they were using them. So they originally were delighted to have these plastic nets, which didn't break down rapidly. But of
yeah,
course, that creates another longer term problem.
which is what, growing hemp?
No, the longer term problem is the fishing tackle and stuff that gets loose from the fishing
Oh,
boats,
okay,
then
okay.
persists in the ocean for a far longer
Yeah,
than.
yeah. Okay. Well, what makes a plastic compostable?
So basically it needs to have carbon oxygen bonds. That's the chemical explanation. You need to have carbon oxygen bonds in the backbone of the molecule, which microbes can actually bite into and break down. And so we can design polymers that have that property. Um, whether they break down naturally in your backyard or whether they require an industrial composting facility depends on the precise structure. And often the crystallinity of the polymer determines how quickly it breaks down.
Hmm. So maybe can you explain to us then the industrial process, the industrial composting? I mean, what goes on there?
Well, so industrial composters uh, they have to be populated with certain types of microbes that are capable of chomping into these compostable plastics. And they have to be maintained at a slightly elevated temperature, about 60 or 70 degrees Celsius. That's hotter than your backyard composter ever gets, which is why you could put these compostable plastics in your backyard or see them out in the environment and they will persist a very long time. They don't actually break down much faster than conventional non-compostable plastics if
Hmm.
they're not in that kind of special industrial composter environment.
Okay. And I mean, my understanding is that there's still a lot of contamination left behind. I guess that's because other kinds get mixed up into the raw material that goes into the composters. But there are plastics that require industrial composting. What kinds of plastics are those? Just for the benefit of our
Yeah,
listeners. I know there's particular categories, and I can't remember
right. So
the
the most
names.
the most widespread one is a plastic called polylactic acid or
Yeah,
PLA.
right.
PLA. And you can make disposable tableware out of PLA. It's a little bit flimsier than the stuff that you make out of the conventional fossil plastics, but it's serviceable. It's just not going to break down under ordinary conditions in the environment. It has to break down at 60 or 70 degrees in an industrial composter. And you're right, it's very difficult to keep it completely separate from other kinds of plastics. And of course, there are additives in it as well. So it's not a pure material either.
Okay, and then plastics that can be decomposed at low temperatures.
So
What are those?
this is a different class of materials called polyhydroxyalkanoates. So the poly always indicates that it's a polymer or a plastic. And then the specific molecules that make up the plastic are molecules that come from algae or bacteria that can be designed to decompose much faster. So they basically just have a different chemical structure.
Mm-hmm.
Of course, low temperature composting is ideal for certain applications, but it also means that your material, your plastic, is not going to be as robust.
Mm.
And that's always the tricky part, that people want their plastic to not decompose until they want it to decompose. and keeping those two things separate becomes very difficult.
So what you need to find is some kind of plastic with a timer in it, I guess, right? That
Or
at some point it starts to eat itself. Uh,
right, a
so
trigger or
a
a signal
trigger.
that causes it to decompose.
Yeah. So we've heard a lot. We actually had somebody on the show who was selling biodegradable cups. I think that was their goal was to replace the big red beer cups.
Mm-hmm.
Um, and it was, I think the cup was made of some kind of biological material. So I mean, I know that everything, since everything is carbon, presumably you can make chains out of that stuff. How does that happen?
So, well, these polyhydroxyalkanoates can be made chemically in a lab, but most of the time they're made biologically. So you genetically engineer microorganisms that make these plastics, and they're
Oh,
made of carbon, hydrogen, and oxygen. Um, they are expensive to make, so they might be 5 times or 10 times as expensive as a polyethylene or a polypropylene, and it's true they do decompose in the environment within months, I would say, which might be a good thing, especially for applications of plastic where you can't keep them out of the environment. There's some places where they're used where that is absolutely the case. But I don't actually like the idea of targeting beer mugs for compostable plastics, because it suggests that it's okay to discard your cup in the environment because it's going to decompose there. I don't think we want to encourage that kind of behavior either.
well, I mean, we want to encourage reusable mugs, right? Or people carrying around mugs like they carry around water bottles. I mean, I've tried to push that idea as well. But somewhere you mentioned the idea of finding some kind of biodegradable material to replace the plastic that's put on strawberry fields.
Well, so there are agricultural films which are used to um, suppress weed growth
Mm-hmm.
and heat the soil and promote plant growth. These materials, because they're out in the sun all day, they do weather and they form shreds. It's very difficult to get them all back again, and it's impossible to recycle them. For those kinds of applications, one wonders if a compostable material wouldn't be ideal. In that case, exactly how long you need it to last, one
Right.
growing season, and you know that you don't want to reuse it, recover it. And so those kinds of materials do leak into the environment. That seems to me like a reasonable target for a compostable or a biodegradable plastic.
Is anyone working on anything like that you know of?
Well, people are working on these polyhydroxyalkanoates. It's, the problem is getting the materials properties right. That's one part of it. That's the scientific problem. The economic problem is that they just cost a lot more to
Mm,
make.
mm. So there's no real incentive there to do that.
Right. And it would have to be a regulation probably that said you must use this material.
You know, or some way to make it more expensive to use the current stuff,
Yes.
which would make strawberries a lot more expensive, I suppose.
Which would make your food a lot more expensive. Yes.
Yeah.
And of course, you would have to be very careful that any of the decomposition products of these plastics didn't actually affect the food that you're growing nearby.
Yeah.
So you'd
So
have to study that as well.
problems and problems. Um, a few years ago, your research group at UCSB published a paper entitled "Degradation Rates of Plastics in the Environment." Can you summarize what you found?
We were looking at what is known about how fast plastics decompose. And we were looking at articles in magazines and newspapers saying plastic bags live for 50 years or 100 years or forever. And we were wondering, how do people actually know that? Because these materials haven't been around that long. So we did a study of the literature. This is my students who actually inspired
Yeah.
this. They wanted to go out and look for the information. There's studies of people who would take plastic bags and bury them in the shallow water on the beach and come back a month later and retrieve them and weigh them again and see how much weight they'd lost and sort of take that as an indication of how fast the plastic was decomposing. We, looking across a lot of different studies, decided that nobody actually really knows how fast these things decompose, because it is not possible within a month or even a year to get an appreciable rate of decomposition that allows you to do a reliable extrapolation. So we actually did some extrapolations as well and said, well, if you make one assumption, you could say 100 years. If you make another assumption, you'd get 2,000 years. So it was kind of a wake-up call that we don't really know how long these things live in the environment. We also looked at degradation rates of some things which are supposed to be degradable, and it turns out that they don't actually decompose a lot faster than plastics that are not designed to be degradable, unless they're in very specific environments. So, if plastics end up being buried in a landfill or not exposed to light, not exposed to heat, they could last just as long. They decompose just as slowly as regular fossil-based plastics.
Well, I know that I tried putting those biodegradable plastic bags, the green ones, in my compost bin, and all I got out were shreds of, those biodegradable bags. They didn't seem to actually break down.
Right. Yes. So you may have just contributed to more microplastics by.
Probably, right. I mean, I don't grow food in my garden, so it doesn't, I suppose it doesn't matter. You're listening to Sustainability Now. I'm Ronnie Lipschitz, your host. My guest today is Professor Susannah Scott from UC Santa Barbara, who works on catalysis, in particular of carbon chains, which is to say plastics. Can you tell us some more about the kind of research that you're doing, Susanna?
I started my career many years ago designing catalysts that would make plastics and be able to design different types of plastics, make them efficiently and cheaply. Now, in my field, the frontier area is unmaking the plastics, right? We want to
Right.
turn them back into raw materials that we can reuse to make new stuff. And the idea is, if you're going to incur costs to recover waste plastic, to sort it, to clean it up, and get it ready for some future use, that future use needs to add value. So we don't want to downcycle the plastics. We want to make something which will actually recover the costs invested in having to recycle. And that's a big problem for the recycling industry, as we currently have it in the United States, is that there isn't an economic incentive to do it.
Mm-hmm.
So we try to create those incentives. At the same time, we're thinking about, if you're gonna invest a lot of energy in using carbon dioxide as a carbon source for making materials, and that's a very it's a very stable molecule. So you have to put a lot of energy in to convert it into something organic that you can make a plastic out of. If you have to do that, your plastic is going to be very expensive. What you'd rather do is recycle the plastic multiple times before it eventually gets converted back into CO2, and then you have to reduce it again to make the plastic again. So this is what we call circular carbon, and a circular carbon economy would not take fossil carbon, turn it into a material, and then after a single use, you throw it away. A circular carbon economy would take these organic materials and use them multiple times with, some inputs required to create them in the first place. And those inputs would be things like renewable energy, renewable CO2, and the waste would occur once every 5 cycles or 10 cycles rather than every single time you make a material. So this is a big challenge because we have to take these very strong molecules apart again. We have to disassemble them into their component pieces. and then reassemble them. And that is a scientific challenge that requires some energy, some chemical inputs, some catalysis. It's a brand new set of chemical processes that we have to re-engineer because they will be different from the ones that originally had us making plastics from fossil carbon. But I really like this idea because I think ultimately we don't need to be extracting fossil carbon in order to make these very useful materials. If we can give them value at the end of life, it kind of solves two problems at once. It displaces the fossil carbon that we originally used to make these materials. We don't need it anymore. And it keeps them out of the environment because who wants to throw away things that are valuable? You want to recover those. The companies that made them will want to recover them.
So how do you go about doing this? And
Well,
in layperson's terms, obviously.
sure. So first of all, you have to decide what is it that you want to make. And you can take a used piece of plastic and say, what can I turn this into? Can I turn it into the building blocks of a new plastic? Can I turn it into other kinds of molecules that can be used to make soaps or detergents or um, other kinds of organic fibers? All of those kinds of things are possible targets. But once you know what kind of chemical transformation needs to happen, you need to be able to figure out how to break the bonds and reassemble them selectively to make the material that you want to make. So
I
one of the areas that I have worked a lot in is making surfactants out of
Yeah.
waste plastic.
Uh-huh. And how do you do that?
That is a reaction that requires redistribution of the hydrogen. So the plastic chains are long chains of carbon,
Right.
but decorating the long chains of carbon is a lot of hydrogen. And if you can take the hydrogen from one location and put it in another location, all of a sudden you have new molecules. The molecules can be shorter, they can have different properties, but we can actually target things that right now the chemical industry makes from fossil carbon, but instead we're making them from recycled carbon.
So this is like soap, right? Or
We can make
detergent.
soap, yes.
So I'm sort of curious, and how exactly do you take the hydrogen and move it around and turn it into something like soap? Again, right? This is chemistry far beyond most of us.
Right.
Um, and the idea that uh, given our discussion about the lifetime of plastics, right? Now, this seems counterintuitive.
So these are very stable molecules. Plastics are very
Right,
stable,
right,
right?
right.
They're
Yeah.
designed that way. Many of their applications, that's precisely what we want. So this is where the catalyst comes in, and a catalyst is a substance which actually breaks and makes bonds. So
Hmm.
if you know it costs energy to break a bond,
Right.
and that doesn't happen spontaneously. But if you break a bond and you make a new bond at the same time, overall the energy penalty is very small.
Hmm.
So the catalyst will remove hydrogen from the plastic and store it on the catalyst.
Okay.
And then when it transfers the hydrogen back to the molecule that it came from, it puts it back in a different place. And it creates a pathway to do that that doesn't have a high energy footprint. So
Hmm. Hmm.
that means that you can actually target the products that you want to make out of the original plastic.
So, I mean, I guess that raises the question: what's the chemical structure of soap? Okay. I mean, this is where I'm having a little bit of conceptual difficulty.
Right. So
Right.
imagine a polyethylene molecule that has 10,000 carbon atoms in it.
Yeah. Yeah.
If I want to make a soap molecule has 20 carbon atoms in it. So one thing that I definitely need to do is cut this very long chain into small pieces.
I see.
Okay.
Okay.
I'm
Okay.
going to do that using hydrogen. Hydrogen will allow me to cut the carbon-carbon bonds and cap them with hydrogen. Where does the hydrogen come from? It comes from this molecule.
Hmm.
And,
Hmm.
and I do that by taking hydrogen out of the molecule and making rings. And the soap molecules have rings in them.
Okay.
When I make the rings,
So
it
instead
generates
of
the hydrogen.
instead of strings, it's rings.
It's rings. Yes.
Uh-huh. Okay. And well, since we're on this, I mean, what is it, the property of the structure that makes it, slippery and useful as it is. I'm just, again, I'm a little bit sort of
Yeah.
at
So,
sea
so,
about this.
so no, a soap molecule actually has a long greasy tail. So
Uh-huh.
that's actually the polymer-like part, the non-polar chain. So we retain a little bit of that.
Uh-huh.
And then it also has uh, a polar or hydrophilic part of the molecule so that it actually dissolves in water. And these
Uh,
these um, sort of schizophrenic molecules, which have a polar component and a non-polar component, organize in the water, and they actually accrete the greasy dirt molecules by solubilizing them in the water. So it's a special kind of molecule that is very carefully designed, and it's just carbon and hydrogen, and sometimes oxygen, sometimes sulfur. But you can design a lot of these different soapy molecules, and you can make them from waste plastics.
so aside from the obvious problem of the world sort of filling up with soap, kind of like Kurt Vonnegut's Ice Nine, I suppose, why can't you just turn all plastic into soap, and decompose it that way?
Yeah, so two issues. One is that the soap molecules biodegrade.
Yeah.
They're small enough. 20 carbons is small enough that microbes will eat them. Okay.
Uh-huh.
So it's not like plastics with 10,000 carbon atoms. Microbes cannot eat that. So you don't build up soap in the environment the way you build up plastics in the environment because they decompose much,
They
much faster.
mm-hmm.
They do. Now, the one problem with my strategy, though, is that we make far more plastic than we need soap. So soap is not the entire solution to the plastics
Oh,
problem. It's only one small part of it.
no,
But
I get that, right? But it was more of a question of if this is a way to use catalysts to decompose plastics, there must be other things you can turn the plastics into that might also be useful and decompose in the environment, right?
absolutely. So, and yes, and I and many other people now are working on targeting all different kinds of carbon-based molecules that are currently made from fossil carbon that instead we could make from recycled carbon. And once
Mm-hmm.
once we do, we will have a way to reuse this carbon and keep it in the economy longer.
And and I guess as a final point, though, that will cost more than the virgin stuff. That will still cost more. I mean, what would it take then to bring the cost down to competitive? I know you're talking about value, increasing the value
Right.
added, but
Yeah.
still, the one goal might be to reduce the cost of this kind of processing to make it competitive. I mean, is that
Right. So
feasible? Potentially
these
feasible?
these soap molecules actually cost more than polymers. So that's
Oh,
a good thing, right? We're upcycling, we're making
uh-huh,
something more
yeah.
valuable. But we still want to reduce the cost. We still want it to be, economically attractive. And actually, um, the soap molecules that we're making are actually better made from plastics than they are made from fossil carbon, right? We don't have to build up the molecular weight. We can get any number of carbons we want by just deciding how many bonds we want to break in the polymer.
I see a fantastic market for that kind of product. So soap made out of plastic, right?
Well, so
I
what we say is we would like the bottle that the soap comes in to be made of recycled plastic, and we would
uh-huh.
like the soap inside the bottle to be made of recycled carbon as well.
Oh well, I sure hope you're successful in pursuing that because uh, even if it would make only a small impact on the total, it would make a lot of people feel much better for what that's worth.
Well, hopefully it's one of many solutions that when you put
Mm-hmm.
them all together would actually give us a circular carbon economy and would make it possible to use all of these materials without
Yeah.
creating the impact on the environment that they are having today.
Yeah. Is there anything else that we should cover that we might have left out, or have we been pretty comprehensive? Anything you'd
I,
like to add?
I think that we do need to think about what these materials are going to cost, what people are going to be willing to pay for them, what kinds of incentives and regulations we can lobby for that will jumpstart these new industries and make it possible for them to get going, and costs come down once industries get started and manufacturing ramps up. So we need all of those things together.
Okay, well, Dr. Susannah Scott, thank you so much for being a guest on Sustainability Now.
It was my pleasure. Thank you, Ronnie.
You've been listening to an interview with UC Santa Barbara chemistry professor Susanna Scott about the chemistry of plastics, recycling, decomposition, and compostability. If you'd like to listen to previous shows, you can find them at ksquid.org/sustainabilitynow and Spotify, Google Podcasts, and Pocket Casts, among other podcast sites. So thanks for listening, and thanks to all the staff and volunteers who make K-Squid your community radio station and keep it going. And so, until next every other Sunday, Sustainability Now.
Good planets are hard to find. Temperate zones and tropic climates.